Well, everyone, this is not going to take up a whole lot of your morning. The concept I'm going to talk about this morning is really not complicated. Anyone can do this, a little practice, and you'll be an expert in no time at all. And the reason I wanted to bring this out is because it's something I preach to people all the time when we're doing tech support. Everyone wants to jump to the gun, and it probably dates back to the early days of tech support when people really didn't understand what could possibly be going on. So they always knee-jerked back to pull the charge. It was like the most common thing tech support might tell you to do. Unit's making a noise, pull the charge. Doesn't seem to be working, pull the charge. Pull the charge, pull the charge, pull the charge. Let's make sure the charge is right. Why? Because you can't be sure the Mitsubishi system is charged right unless you actually weigh the charge. But we could avoid a lot of work, especially in bad weather situations. Who wants to be outside building a tent to try to stay out of the rain while they pull a charge? I would rather have guys learn how to do a BTU calculation on the output of the unit to verify that there isn't a charge problem. So if a unit has a certain rating for a BTU output, if it's actually exceeding that rating or meeting the rating, I don't think you want to pull the charge. It's probably something else that we may have to look at. So that being said, let's get started. So here is the basic formula for sensible heating or sensible cooling. Now, the sensible part comes into play because we're not talking about changing the moisture content of the air. All we're going to be doing is heating it or cooling it and dropping the actual temperature, meaning something that you can measure with a common thermometer. So anyone who is not muted, please mute yourself so we don't hear any background noises. We would appreciate that much. So again, it's just the sensible formula. If you want to take a snapshot of this with your phone, go right ahead. This will be available, I'm sure, on Gensco Customer as a replay. You could watch it another time. We are recording this. So if you're a service tech, at some point, you should have these kinds of stuff memorized. So the formula for sensible heating or cooling is the CFM passing through the unit times the difference in temperature times a constant of 1.08 at sea level. Now, if you are not at sea level, there is approximately a 4% D rate for any output based on each 1,000 feet of elevation. So if you were doing something in Missoula at 3,000 feet, whatever you do in this formula will be reduced by 12% as an actual output. So CFM times 1.08 times the difference in temperature between the return air and the supply air. And where does that 1.08 come from? It's from the specific heat content of dry air. 0.075 pounds of air per cubic foot of air, because again, we're dealing with CFM, and 60 minutes in an hour because we are dealing with BTUH, how many BTUs the systems produce in an hour. So the first place to do, and our example this morning is going to be using an MUZ MSZ GL wall-mounted unit because it is pretty simple. First place I want to do is go to mylinkdrive.com. Unless you already know this number, you need to find out what the CFM rating is of this unit. And I'm using a ductless unit. Because there's no ductwork, you don't have to worry about measuring the air. You can go to the submittal, and if that unit is clean, filter's clean, coil's clean, blower's clean, then the rated airflow when we choose, and we're going to be doing this with high-speed fan, should be pretty close to what it actually is doing. And when it comes to ducted units, towards the end of this presentation this morning, I will talk about what you have to do to actually measure CFM on a ducted unit. You can't really use the ratings. There are a lot of factors that are involved in what that unit's going to actually produce. So again, we're going to use the MSZ GL12 with an MUZ GL12 outdoor unit. When I go to the submittal, here's my capacities. The rated capacity is the one I'm concerned about. This is the one that legal document. This is what the unit should produce. And if you produced it correctly, this is what we guarantee you to get. 14,400 BTUs. If I go to the airflow section, I want to look at the high-speed fan. And then since our first example is going to be doing a heating output check, it's going to be a dry coil. There will be a different CFM number for a wet coil when you're running it in cool mode. And you'll see that in a little bit. So we find out what the actual unit's rated for. We find what the high-speed fan is rated for. Verify the unit is clean. So the 406 number is the number we're going to be sticking in this formula when we do another step. Now, this is what equipment, when you're talking about how it's rated, where did that rating come from? A lot of people aren't aware that in cooling, that output rating, if you're doing a cooling check, was done at an 80-degree return air. And it's very rare that your customers are going to have a set point of 80 degrees. If you actually reduce the temperature in the space to say their normal set point, it's 73 maybe. The output that is listed as the cooling rating will actually be less than what it's rated, because at 72, I have less heat to work with. Out in the outdoor, 95-degree air. Now, if the air is cooler, that does not derate the unit. But if you're living somewhere on the east side, the mountain area, the desert area, you get above 95 degrees, you begin to derate the output of that unit. In fact, once you exceed 100 degrees, the derate starts to escalate, and it can get very substantive. You hit 105, 107, you may have lost 15, 18% of your cooling capacity. Heating units are rated at a 70-degree return air temperature. And of course, outdoor temperatures are 47, you'll find a rating, and generally at 17, you'll find a rating. Another place to check what this system would possibly output would be to use Mitsubishi's Diamond System Builder. If you're familiar with it, you can actually put in the actual temperatures that you are experiencing today, the actual return air temperatures here on the right, outdoor temperatures here, and in this example, 32-degree outdoor air, 74% humidity. I've got an indoor temperature of 68 degrees, and I'm at 1,225 feet of elevation. This is what the Diamond System Builder says I should be getting out of that unit for heat at those conditions. So this is another way, other than just the submittal, if you really want to be 100% accurate, to see what the output should be. Now, our actual test, we're going to turn this unit on in heat mode and set the set point as high as we can, because if we can get it more than 4 degrees from actual temperature, the unit will go to full speed. So we're going to set it as high as we can so it doesn't satisfy or get within that 4-degree band from the actual temperature. We're going to allow this to run for 15 minutes, and we're going to keep that fan on high speed. Now, we actually take a measurement at the end of that time period, 15 to 20 minutes. This is our results. We have a 69-degree return air. We have a supply air of 108 degrees. If we throw that numbers, the difference of that number is 39 degrees. We're going to put that in our formula. From our submittal, our CFM was 463 CFM. We have our constant of 1.08, and then our temperature difference, our delta T, was 39 degrees. We put that formula together and it results in a BTU-H output in heating of 20,502 BTUs. Now, if someone was complaining they have insufficient heat, this obviously dispels any thoughts that it's a unit problem. It could be the house is too large for the unit. Don't want to say the unit's too small, but that could be a possibility. Or in the case of, this is an actual job site visit I made, these numbers came from. This was a house that someone had a lot of high back furniture about 12 feet in front of this unit and prevented the heat from going any further in the house, which produced their complaints. The unit didn't have a problem heating. It had a problem heating where they wanted it to go. So that in a nutshell is a sensible heating, or this could have been a cooling sensible calculation. Now that is pretty simple, actually. You do that a few times and you're a pro. Cooling is a little harder. You're going to need more tools. You're going to need a little more practice and some knowledge of psychrometrics, the properties of moist air. This is the formula for doing a total cooling BTU-H calculation. It's similar to our previous sensible in that we still use CFM. We still have a constant. In this case, it's 4.5. And we're going to be dealing with the difference in enthalpy of the air coming in and the air going out of the unit. The enthalpy is the BTUs per pound that's actually in the air. And we want to see a difference of that enthalpy. And we're going to show you that calculation shortly. So again, this is for sea level. The 4.5 is a constant. That comes from 0.75 pounds per cubic foot of air, average for 77-degree air at sea level, and 60 minutes, because again, we're dealing with BTUs per hour. And CFM is dealing with cubic feet per minute. So what is the delta H? Again, that's the difference in enthalpy, amount of BTUs are actually in the air per pound of air. We're going to turn the unit on again, just as we did in heating, and we want this unit to go as low as we can in cooling. If the room is already fairly cool, you would probably want to press the emergency op button on the front of this unit one time to put it in cooling test mode, so it will stay running and not reach the set point. It'll run in that mode for 30 minutes, and it will not care how cold it gets in the room. So if you're doing this in cooling and it's already cool, you may want to use the test button. Otherwise, just setting the temperature as low as it can go may not be long enough runtime. And again, we want to allow at least 15 minutes for the outdoor unit to speed up and get to its steady state efficiency before we take any temp readings. Now, to do a total cooling, you're going to need more than just a thermometer. You're going to need something that can also measure humidity or wet bulb temperature, something that can tell you the actual conditions of the air. And we're still doing an MSZ, MUZ system. These are the results we got using a psychrometer. 75-degree return air at 54% relative humidity. And our supply air was 51 degrees with a 78% relative humidity. Even though we're going to be removing moisture from this unit, we are condensing the air and making it more compact. And thus the water that remains in the air after it passes through the unit is going to produce a higher relative humidity, even though it is actually less grains of moisture. This confuses people sometimes, but that's the actual fact of what can happen. Now, if this return air temperature or humidity itself was much higher than this, the higher that return air humidity is, the higher the humidity is going to be on your exit side. And this could be a clue when you're dealing with a unit that maybe has a mold issue. And everybody has, or is it, at some point may have run into this, where you've got mold growing on the blower wheel inside a ball head unit. It's probably due to very high humidity conditions within the space. I've seen the supply air humidity as high as 95, 98%, because the humidity in the room was high. And incidentally, the goal for our humidity for someone's comfort level within a space is about 50%. 45 to 50% is the ideal range for that to be at. So for this calculation, again, we're going to need a psychrometer. And we take these measurements, 75 degree, 54% relative humidity, 51 degrees, 78% relative humidity on the supply side. And we're going to have to use a couple of more tools. That can either be a psychrometric chart you see on the left, or a psychrometric app on your smart device. Now I have both, but I prefer the app because it's really easy to use right there on my phone. This would be an example of actually plotting the temperatures that we just measured on a psychrometric chart. 75 degree dry bulb, 51 degree exit air, and our humidity points, 54%, 78%. And when we intersect the vertical dry bulb temperature line with the horizontal BTU line, here is my BTUs per pound, and the difference between my two red lines here on the chart, this is my delta H. If I'm using the app, I can enter dry bulb temperature, relative humidity. It will tell me quite a bit about what's in that air. And my exit air, my supply air, dry bulb, and relative humidity. Again, everything I need to know about that air. So there are the actual readings that I just measured on that MSZ GL12. And my enthalpy, or the BTUs per pound, return air, 28.93, enthalpy of the supply air, 1892. I'm going to subtract the supply air from the return air, and I am going to come up with a delta H, or change in enthalpy, of 10.01 BTUs per pound of air. Now we're going to have to use the wet coil CFM from this, because once we start running this in cool mode, 15 or 20 minutes, the coil is going to become wet, and it's going to be a little restrictive to airflow that we don't have when the coil is dry, like in heat mode. The rating for a wet coil, 364 CFM. We're going to throw this in our formula, 364 times the constant, 4.5 at sea level, times our change in enthalpy, 10.01, and the result is we are producing 16,396 BTUs total cooling. Again, this will be available for review later, but if you want to take a snapshot of the formula and an example of having it worked, go ahead. Now, cooling can get pretty interesting. So we've done this test. What is my percentage of actual latent cooling? The amount of air conditioning that's being utilized to dehumidify the air. If I take this formula we just calculated for total cooling, and I use the same numbers we measured on the dry bulb side, 75 degree return air, 51 degree supply air, which had a 24 degree delta T. And I put that in the sensible formula, 364 times the constant of 1.08 times the delta T of 24, I get 9,934 BTUs of sensible cooling. This is the actual cooling BTUs that's going to drop the temperature in the room. But the amount of cooling that's actually removing moisture is going to be the difference between the 16.3 and the 9,009. So if I subtract 9,934 from 16,396, I end up with 6,462 BTUs of latent cooling. This is the amount of BTUs that's actually removing moisture. And if I take that number, 6462, and I divide it by the 16,396 total cooling, it tells me that my latent cooling percentage is 39%. Now, if you actually come out with a number like that, that's high. All these units have ratings to do latent cooling somewhere in the 20 to 25% range. So when I actually do one and see a number like this, I know my humidity is a little high in this space. This could be for many reasons and probably something we could cover in a future quick hitter. But this would alarm me if my actual latent cooling was that high. I've got an obvious humidity issue in the house, and it's either from internal lifestyle, or it's because my unit may be too big and it doesn't run long enough to actually get the moisture out of the air. And that, by the way, is probably going to be a good idea. I'll work on something on that for after the first of the year. So look for maybe another one of these quick hitters where we talk about how to deal with humidity issues. If anyone wants to take a snapshot of this as an example, you can review later, please do. Okay. Now, what if we have a ducted unit? It's going to get extremely complicated. You're going to need more tools. If we go to the submittal, and in this example, I'm going to be using one of our most common units out there, the SVZ multi-position KP30. It has a high-speed fan rating where it's rated at of 875 CFM. If I go to the service manual and look at the blower chart, the actual CFM output can depend on the actual static pressure. So from the unit, from the factory, this unit came with a set point of 0.5 inches of static pressure. If I measure my static and it's actually 0.48, and I've made a line on the blower chart, anything within these dashed lines is valid numbers. Anything outside of those dashed lines are maybe, maybe not. So if I follow my actual static pressure line over to the high-speed fan curve, and where it intersects with the curve, goes straight down, this puts my actual CFM somewhere in the 920 CFM range. Now, this would be okay to use for a ballpark, but it's not going to be 100% active or accurate, because there is a little known phenomenon called the system effect. The system effect has to do with how air actually enters the blower and can be caused by things like ductwork fittings right next to the furnace, one side tap, insufficient space, straight duct horizontally before it side taps in order to allow it to be uniform, enter the blower uniformly. They can all have an effect on the actual air that's coming out of the unit versus the blower chart. But to measure static pressure, you want to be as close to the blower as possible and between the blower and the filter, and then on the exit side of the unit. If you're doing this on a unit with a cooling coil, you have to be between the furnace and the coil. If this is say a gas furnace, but if this is a Mitsubishi SVZ, you want to be on the outlet side of the furnace, of the air handler. And if you've got an electric heat strip, by the way, you have to take this measurement between the outlet and the heat strip, because the heat strip is going to have a pressure drop. In order to get an accurate total external static pressure. In this example, our supply static was 0.13. Our return static was a negative 0.35. We add 13 to 35. This is where our total external static of 0.48 we used in the blower chart example came from. Plot that again on my chart, and it says about 920 CFM. But again, the system effect can make this inaccurate. But if you're just trying to get a quick measurement, this ballpark will be probably sufficient. Won't hold up in court, however. To do something that's going to hold up in court, you're going to have to actually measure the CFM. Myself, I may measure this and get a number, and then I want to double check that with an actual measurement. So how do you measure it and determine how much CFM the unit's using? This is another formula. This is a simple airflow formula. The CFM that any unit or is passing through any point in this unit will be the area of that point times the velocity of the air in feet per minute that's going through that opening. And in our case, and what I'm going to do on an actual job site visit is use the return air grill. If I've got two, then I'm going to be doing two of these measurements. But the CFM will equal the area of the opening times the velocity of the air going through that opening. If you want to take a picture of that formula. So how do we measure the air? First, we need to know the actual opening of the grill. We'll take side A and multiply it times side B. And this is, for an example, a 20 by 20 grill, but it doesn't have an opening 20 by 20. The actual inside opening of this grill is going to be 19.25 by 19.25. Yours may be slightly different. You could have 19.5 by 19.5, but you get the message. It's the actual inside opening. So I've got an actual opening of 19.25 by 19.25. That equals 370 square inches. But the actual free area of that grill is going to be that less all these louvers, which take up about 10% of that area. So my 370 minus 10% leaves me with 333 square inches. I'm going to divide that by a square foot, which is 144 square inches, and I'm left with the number we want, 2.31 square feet. The airflow formula works in area, which is in square feet, times velocity, which is feet per minute. So after I have determined the area of my grill, the free area, next I'm going to need something that can measure velocity. In this case, an air vane velometer. And with a grill that's 20 by 20, I'm going to take a bunch of readings across this grill and get an average of the air that's going through the grill. The geometry of what's behind this grill can cause the velocities to be drastically different in different parts of the grill, depending on what kind of ductwork, where the ductwork takes off. All those things come into play. This is why you need as many measurements as you can to get an accurate number. In the case of a 20 by 20 grill, I'm going to take 16 measurements, 4 across and 4 down. I'm going to stick my velometer on the grill, wait for it to steady, record the numbers. Something like this. Once I've done that, these numbers are going to go in a formula. These are my average velocities in feet per minute at the 16 different points of the grill that I've measured. The sum average of the 16 points is 343.75 feet per minute. I already know the area of my grill, so I'm going to put this into the airflow formula. 2.31 square feet times 344 feet per minute. I am pulling 795 CFM through that grill. This is a little more work involved to do an actual BTU calc on an air handler, because you're going to have this extra step of figuring out how much CFM you actually have. But that is the way to do it. So if you want to take a picture of this as an example, here are the formulas again. If you want to take a picture of them all together. If you are trying to do a cooling check and you don't have a psychrometer, you can use a thermometer to do the sensible cooling. just the temp split times the CFM times 1.08 and add 25% to it. You'll be in the ballpark. It won't be 100% accurate, but you'll be close. Because again, most units do about 25% latent cooling. But this could save you from spending a couple hours in the rain or the snow, driving wind, pulling charge to find out you're 2 ounces low, not 2 pounds. So I'm not concerned about 2 ounces. And if it doesn't do the BTUs that it should have been doing, it's time to pull the charge. That being said, anyone have any questions?
I do have a question, if you can hear me.
I can.
Yep. So you only need to get the relative humidity when you're measuring in cooling mode to get the, is that correct?
Yes. If
Okay.
you're using an app, you can put either relative humidity or wet bulb or
wet
dew
bulb.
point in to come up with the actual numbers.
Got it. Okay, that was my question.
Easy question to answer. I like humidity because it's something, you know, it means something to me. I understand if I see a wet bulb number that approaches the dry bulb number, but I'd rather see the humidity percent because your homeowners understand that. They don't understand what wet bulb is. You can see also where it displays the dew point temperature. In the case of this picture here at the top, our return air, our dew point's 57. Why is that handy? That's going to be the temperature of something in the room, like say a glass of iced tea. That's below 57. It starts building condensation on the outside of the glass. Same thing about our coil temperature. In order for us to actually condense and remove moisture, the coil temperature has to be below 57 degrees. This could also be why water is dripping off the front of your unit while it's running, because the dew point temp in the room is 57 and the exit air is 51. My louvers are much colder in the front of that unit. Eventually, over a little bit of time, they'll reach 51 degrees and any moisture in the room will start to build up on them. So these are good numbers to use. And if you don't have a psychrometer, you can get a nice digital one for $100 or less.
Hey, can you hear me?
Yes.
What is the name of the app you're using to calculate that?
Psych Plus by Carmel Software. If you go to the App Store, you're probably going to find 50 different apps on that can do psychrometric measurements. Carmel does a lot of stuff for the HVAC industry. They have lots of different apps. If you don't have the Psych app, there is a way to come up with these numbers using formulas, but that's probably an 8-hour class. The app makes it so easy. But there's the app. HVAC Psychrometric Lite is one of them. There's also one that's not light, has a little more features in it, but the light one is perfectly fine for what we're doing. And that is the one where these numbers came out of. Notice here also specific volume of air that's shown here. In the return air, it's 13.68 cubic feet per pound. And in the supply air, remember I said it got denser, it's 12.99 cubic feet per pound. If we were going in heating mode, the supply air would be higher than the return air. This is why if you're on a ducted unit and you want to do air balancing and you want to measure CFM, in fact, for this particular exercise, you don't want the unit running in heating or cooling. You want it to just be in fan mode so there is no state change of the air as it goes through the unit.